Thank you very much for the introduction. Great to see you all. Yeah, welcome to the last lecture in this series on Introduction to Interior Point Methods for Discrete Optimization. We'll continue as we have the last few with where we were at the end of last lecture. So just to remind everyone, the goal of these talks in general, which I hope you will feel like we have achieved to some degree at the end of lecture today, were to survey some of the recent advances that have happened in using interior point methods to get faster runtimes for solving a range of continuous and discrete optimization problems. Last lecture, we were primarily covering in greater detail some of the fundamentals of interior point methods, how you design and analyze algorithms there. And the goal for today is to wrap up some of that coverage of sort of classic interior point theory and give a taste of some of the newer components of interior point methods over the last 5 or 10 years. So that's the plan. So today we'll be wrapping up what we were covering last lecture on interior point method basics, or sort of classic fundamental theory for path following interior point methods. And what we'll be doing today is covering some more recent material over the last decade on getting improved convergence rates using Lewis weights, on primal dual methods and robustness. And as we get towards the end of the class, we'll be a little more high level, but please ask me questions along the way on anything as it should arise. So to be a little more concrete, our plan for today is as follows. First, we'll start with a bit of a brief recap of what we covered last lecture. I'm also going to try to give a little bit of a even more of a geometric picture for interior point methods and the analysis we were discussing. In the second part of the lecture today, we'll talk about how to move beyond things like the logarithmic barrier, which is a standard self-concordant barrier for solving a variety of the problems we've discussed. Try to give a geometric picture for how to improve. We'll talk about weighted log barriers and a new self-concordant barrier over the last 5 or 10 years that can be used to get better rates. And in the last part, we'll then talk about how to make this method efficient and talk about the sort of algorithmic framework that underlies some of the even more recent advances on solving things like max flow and min cost flow and L1 regression and min cost transshipment. This will be primal dual methods and robust methods. We'll discuss a bit more how to make these low iteration interior point methods only require solving linear systems. And I'll briefly touch upon some of the more recent improvements, like how to use two-sided barriers efficiently in this framework and how to implement these methods efficiently to get fast runtimes. So that's the plan for today. Please stop me if you have any questions. Again, I might stop a few times during the lecture and check that you're all following. If you feel comfortable with it, it'd be great for those of you that don't mind turning on your video. It helps me a bit with pacing and what I'm going to cover. And even if you don't want to do that, if you don't mind using those thumbs up signs sometimes so I can make sure people are on the same page, that would be great. Any questions about anything before we dive into the material? All right, plan sound good to everyone? All right, great. All right, so let's remember where we were at the end of last lecture. There were 2 motivating problems we were primarily considering. We were trying to solve linear programs given in this dual and primal form, and we were trying to solve the minimum cost transshipment problem, which was simply the special case of linear programs in this dual and primal form, where the constraint matrix A is the incidence matrix associated with a graph, meaning it's a matrix where every row had exactly 1 + 1 and 1 - 1. We discussed how in that case, linear programs in standard form correspond to computing the best flow that routes a set of demands while the flow is non-negative and some sort of cost on the edges is minimized. Now, the way we were trying to solve these problems primarily last lecture was through path following interior point methods. So these are methods that after some sort of reduction assumed that you have some sort of point in the interior of the polytope. And once you had this point in the interior of the polytope, we introduced some penalty function, penalizing points going to the boundary of the polytope. We use that to induce a penalized objective, which was simply some objective that for some parameter traded off how much we cared about minimizing the cost and how much we cared about minimizing the penalty. We talked about the central path, which was simply the minimizer of the penalized objective for every value of this path parameter mu. We talked about how this path goes from the center of the polytope at mu = 0 to the minimizer of the linear program as mu goes to infinity. And the way path following methods work, as we discussed, the framework we were discussing is once you start with some point that's close to the central path, we would simply repeat the process of increasing the path parameter, taking a Newton step to get close to the next central path point for that path parameter, and repeating. And we were discussing different assumptions on the barrier and what was needed so that we could analyze such a method and show that there's a value of delta mu that just depends on the barrier that we could pick and make this method work. And we discussed how, and we'll prove a bit more today, how this corresponds to a 1 over delta mu iteration method. All right, so let's remember the analysis we had for this last lecture. So last lecture, we derived and motivated a bit the different assumptions we'd want on this penalty function in our penalized objective. And the assumption we derived by the end of the last lecture was what we would assume is that this barrier function P is a new self-concordant barrier for the set, for the polytope, the set of Y where AY is in most B. What this meant was that this penalty function P was a barrier, meaning its value went to infinity as Y went to the boundary of the polytope. We also assumed that this penalty function was self-concordant, meaning we could bound the third derivatives in any directions in terms of the magnitudes of those directions in the Hessian norm. And where this value of nu came from was assuming that the barrier was not too large and that the norm of the gradient in the Hessian inverse norm was not more than square root of nu for any point inside the polytope. The way I maybe think of these assumptions is we wanted P to be a barrier so that all the intuition of the methods we described makes sense. Self-concordance gives a bound on how fast the Hessian of the function changes. It's the assumption that enables Newton's method to converge quickly at different points in the interior of the polytope. And then this value of nu governs sort of a measure of how large the barrier is, how large it actually is at every point in the polytope. And therefore, how much can you increase the path parameter while still being able to converge quickly to the next central path point from self-concordance. All right. I mentioned briefly, there's a much broader theory for the design of self-concordant functions. It's known that every D dimensional bounded convex set has an O of D self-concordant barrier. And we discussed how for the problems we were solving, that there's simple decomposable barriers like the logarithmic barrier that correspond, that have self-concordance N for linear programs like this, or a number of edges for things like minimum cost transshipment. All right. So with this barrier defined, the way we said we'd analyze these path following methods or kind of measure or keep track of the quality of the current point Y in the interior that we're maintaining was through the Newton decrement. And this is simply the norm of one of these centering steps in the Hessian norm. It's also just the gradient, which equivalently is just the gradient of the penalized objective. There should be mu's here. Should be norm of the penalized objective in the Hessian inverse norm. All right. All right, now with this defined.
I was going to say, I guess the Hessian doesn't depend on mu, so the second mu is not actually needed, right?
Agreed. It's agreed. And we use this a bit in the analysis, and that's in part where this definition comes from. That's correct. This is just the same as the Hessian of P at Y, because the Hessian of the linear term of the objective is 0. That's correct. Yeah, so it wasn't as big of a typo as I said. And again, I've been posting the slides, by the way, on the Slack, as you may have seen. I'll post them again today. If you find typos or want things clarified, feel free to ask in the chat, and I'm happy to update it. So just let me know. All right. So with this, how do we say we could analyze path following methods? We showed that self-concordance implies that if the Newton decrement is at most a small enough constant, then every step of Newton's method has more than at least halves the value of the Newton decrement. And we also, I touched upon briefly that when this holds, it implies that you're close to the central path in a number of different ways. Like it implies that your function value is not too large. It also implies that your distance to the central path in the Hessian norm is not too large. So the way we said we could then analyze these path following methods, we assume the Newton decrement is not too large. This was enough that their one centering step would decrease it. And then we argued that if we pick delta to be on the order of square root of the self-concordance, then when we increase the path parameter, when nu is small, it will only increase by a constant. So what this says we can do is we can maintain the invariant that the Newton decrement is always at most, say, a quarter, by simply centering so it's at most an eighth, increasing delta so it becomes at most a quarter, centering so it becomes an eighth, and repeating. And this gives a method where we can follow the central path, never straying too far from it in the Hessian norm. All right. And I touched upon, we proved this in the special case of the log barrier. I'll prove it more generally today, that this implies the fact that we can increase the self-concordance barrier, the fact a parameter by square root nu, this implies a square root nu iteration algorithm up to logarithmic factors. As a quick aside, I think this is very, it's a very nice theorem that this holds so generally for self-concordance. I think it's interesting to contrast interior point methods in general to, say, cutting plane methods, which some of you might be familiar with, or different generalizations of the ellipsoid methods. So those are iterative methods that can solve a convex program in number of iterations proportional to the dimension up to logarithmic factors. And what this theory says, and that's known to sort of be optimal in the worst case, if the only way you have of accessing your convex function is through, say, a gradient oracle, or say you were trying to solve a linear program and you only had a separation oracle, so you could figure out what constraint you're not meeting, and you knew the cost. In contrast, here what we're saying is, and this is this classic insight of self-concordance from this beautiful work of Nesterov and Nemirovsky, that in contrast, when we have enough structure that we can construct self-concordant barriers, in principle, there's always a root deiteration method. So it's saying that if you can get for kind of the right first order, second order information, if you can take sort of Newton steps, you have the right second order, you can improve this deiterate, like the worst case D that happens for convex programming, to root D for these more structured instances where you have barriers. Okay. So that's where we were last class. What I'm going to do today is I'm going to talk first about some additional properties. I'm going to improve this fact. This sort of implies a root deiteration method. I'll talk a little bit more about the geometry of self-concordance, another way of thinking about this. And from there, we'll launch into that geometric understanding to try to improve the root n given by the root n, where n is the number of constraints given by the logarithmic barrier, to root dimension, which could be much smaller. Or if you'd rather think about things like min-cost transshipment, how to reduce the root number of edges iteration complexity to the root number of vertices iteration complexity. Any questions on anything so far? Picture clear? Great. All right, so to start, I want to give a few additional properties of self-concordant barriers. I should point out there's many more properties than those I've been touching upon in the lecture. These are just a few that let us get the sort of immediate claims I want. And the two additional properties are the following. First, claim you can show that if a function is nu self-concordant, then you can upper bound the inner product of the gradient at a point with the difference of that another point in that point by most nu for all points in the domain. Okay, so in some sense, the inner product of the gradient and any direction inside the domain is not too large. I guess it could be very, very negative. This theory is not bounding how negative this could be, but it's never too positive. Right. Now, in the interest of time, so I can talk a bit more high level about some of the pictures, I have the proof in the slides. The proof follows the same sort of very broad template that a number of proofs in this space follow, and a number of the proofs in these notes all follow. You let a point xt denote, you let xt denote the line between x and y. So xt is x plus ty minus x. So t going between 0 and t at 0, this is x, t at 1, this is y. And the values xt for all t give the line segment between x and y. And the proof technique is you kind of pick some thing you want to bound, like grad f of x, parameterize a version of it with t, use Cauchy-Schwarz to upper bound it, compute the derivative of it. When you have the derivative of it bounded, you can integrate the derivative along the line for the right function of it. And with that, do some analysis to show things are bounded. But these general techniques of sort of compute a derivative, integrate, and apply Cauchy-Schwarz, they appear in many, many proofs of kind of bounding how things, different functions behave in this space. So I think it's maybe a good exercise to go through this and try to prove yourself. But that's the main ingredients underneath the proof. This is the proof, but I won't go into further details for now unless someone asks. Similarly, or the other lemma that I want to give about self-concordance is the following. So this lemma says that if the self-concordance parameter, that says that you could upper bound the inner product of the gradient and the difference between any 2 points in the domain of the function by nu. So this says it's not too large. And the second lemma says if it's not negative, the same sort of, I switched x and y, says that if we have a bound on the inner product of gradient x and x minus y, so if we have a sort of I guess this would be a better bound, then you can bound the difference between y minus x and the Hessian norm. All right. And the proof technique is very similar. Consider the line, consider the same potential function, do some algebraic manipulations, look at the derivative, integrate, use bounds we've shown on how much y minus x uses in the Hessian before, do more integration, and you get a bound. Okay, so those are the two lemmas. They'll be in the notes I'll post. What I want to do now is give some interesting, I think, implications of these two nice lemmas about self-concordance, unless anyone has a question about the proofs or wants me to go into greater detail on them. Okay. All right, so what do these lemmas imply? So the first lemma, I claim, implies the following. Suppose we're looking at our penalized objective, and we look at the minimizer of the penalized objective. So we look at the mu central path point. The first lemma says, if we look at the cost of this central path point, and we compare it to the cost of the actual minimizer of the linear program, then its cost is at most nu over mu. So in other words, as we increase mu by alpha, this term decreases by alpha. And this says every time we're doubling mu, we're halving this quantity. And this says that we can bound the error of our point. So this gives a bound on our suboptimality in terms of solving the original linear program as we increase mu. And this is why when I was saying if we can double mu in square root nu steps, then we have up to log factors a square root nu iteration algorithm. All right. The proof of this is rather simple once we have this lemma. So the proof of this is just note that the optimality conditions of being a minimizer here are that the gradient is 0. All right. So the gradient of this is just mu times c plus the gradient of the barrier. And note that the minimizer of the linear program is in the polytope. Just like last class, I'm not going to be very careful with boundary conditions here. So the actual minimizer, if I consider not just the interior of the polytope, but also the boundary, then the minimizer is in the interior. Or you can imagine considering a sequence of points to get closer and closer to the boundary. All right. So what does that say? It says we can multiply this with just the difference of the central path point and the minimizer. And the fact that this is 0 says that this difference is upper bounded by the inner product with the gradient and the difference, just rearranging this. However, this term we bounded by nu, and therefore we divide by mu, we get the claim. So remember I said that self-concordance kind of gave a notion of like how large the barrier is. This is kind of saying since we have a bound on like how large the barrier is, we get a bound on what our optimality is for increasing mu. So this is like quantifying how that like when we a bound on like when we increase mu, how much now our penalized objective has cared about minimizing the actual cost of the linear program versus some contribution from the barrier. This is kind of quantifying that the contribution of the barrier to like the function value gets smaller and smaller as mu increases. All right, and this justifies the root nu iteration bound I said on the previous slide. Any questions on this? All right, second one, let's look at this second lemma. So recall last lecture, we said that if we look at the Deacon ellipse of radius r, so we look at for a point x, we look at all points y that are in most distance r from it in the Hessian norm, this gives some sort of ellipse. And if we pick R to be 1, this is the Deacon ellipse of radius 1, and we prove that for a self-concordant function, the Deacon ellipse is inside the polytope for every single point. In particular, it's inside the polytope if we let y nu be this polytope center. All right. However, what does this lemma say? Well, note that if we're actually at the minimizer of the polytope, okay, so we've actually just minimized, for the center of the polytope, if all we've done is minimize the barrier, we're at this point y naught where there's no contribution from the cost. The optimality conditions of this are that the gradient of the barrier is 0. So in the language of this lemma, grad f is 0, and this condition trivially holds for all points. For all points inside the polytope. And what that means is that all points inside the polytope are at distance at most nu plus 2 square nu from the center. In other words, this says that at the center, the entire polytope is contained in the Deacon ellipse of radius O of nu. All right. So this is a nice property of self-concordant barriers that you can think they're giving ellipses that are always inside the polytope, where you don't have to scale them up too much for them to contain the entire polytope. This property is sometimes called being an O of nu rounding, meaning that it's showing that you can approximate the ellipse up to a factor of nu. Interestingly, this lemma is actually proving something even stronger, because suppose y is any point in the polytope that has cost at most that of the mu central path point. When that holds, these same optimality conditions, you can show that this condition holds. And therefore, again, this point y is in at most distance nu plus 2 square root nu from the point, the mu central path point. In other words, what this says is as we run our interior point method, and we get some point further down in the polytope, if we look at the Deacon ellipse, it's contained inside the polytope. And if we look at all the level set, so we look at all of these points that have value at most y of mu, that's in the Deacon ellipse where we scale it up by a factor of O of nu. So as we run the interior point method, we're kind of maintaining this property that the Deacon ellipse is sort of inside the polytope. It gives us a region we can move in. And this region we can move in is not too much smaller than the region that contains opt. And this property is maintained as we run the interior point method. Any questions on this? All right. So again, from all of this, I just want to recap a little. We showed that the logarithmic barrier is n self-concordance when there are n constraints. So this shows the logarithmic barrier gives an n iteration algorithm, root n iteration algorithm for solving linear programs, and a root square number of edge iterations for minimum cost transshipment. Before we move on to improving the iteration bound, you might ask, one question you might ask is what about maximum flow or min cost flow and some of the other combinatorial problems we've discussed?
Can I ask quickly, Aaron?
Yeah.
Is that on the previous slide? If you go back, yeah. Shouldn't that be y minus x near the top right? You have gradient f times x minus y. Is that correct, or should it be y minus x?
Sorry, here?
Yes.
I will double check before I post the slides.
I'm just sort of pattern matching with the left and also below.
Yeah. I want to double, I'm just scared to do it on the fly. I want to double check if this is correct, and I could have just written that this is at most 0, or I swapped the x and y. I forget if I did it for the proof or not. If you don't mind, I'll check before I post online and have it the right way. But thanks for pointing it out. But yeah, in the interest of time, I guess I'll check at the end before I post. Thanks. Any other questions? All right. All right, so what about minimum cost flow? So remember the min cost transshipment problem, we're trying to get a non-negative flow that routes the demands of minimum cost or maximum minus cost. And we said that the minimum cost flow problem was the same problem where we also just had upbound constraints on every entry of F. All right, so how would you extend this analysis to the case where we have upper bound constraints? So we don't want to just solve this problem where F is non-negative, but we also want F to be at most mu. At least if we're using the sort of frameworks we've seen before, there's actually not too much you have to change. The idea is, whereas the log barrier, the sum of minus log of Fe is a barrier on F being non-negative, if we just also add the constraint, the term log E mu E minus Fe, this then becomes a barrier on this entire region. And it's from theory of self-concordance that the sum of two as you add self-concordance functions, you preserve self-concordance, but the barrier parameter increases. You can show that this is actually also an O of number of edges barrier. So you could run the same method, just replacing the barrier with this barrier function. Essentially, the same analysis would apply. So you need the dual version of everything that I said that handles the linear constraints. And this would also give, this is an O of E self-concordant barrier. So this would give a root E iteration method. And just as we discussed last time, that every iteration of this method is just doing a simple sort of gradient operation. It's just looking at Fe, 1 over Fe and like 1 over mu E minus Fe. So things like computing the gradient and the Hessian of this barrier are easy. The computational work comes from performing projections, which involves solving a linear system. Just like for minimum cost transshipment, these projections are electric flow problems, which can be solved in near linear time with Laplacian system solvers. The same holds here. And this pretty directly, once you have Laplacian system solvers, gives a number of edges to the 3/2 algorithm, as was noted by Deiteration Spielman in 08. So this whole framework without too much work gives you some number of edges to the 3/2. And again, because of the flexibility of self-concordance, if you had slightly different sort of things in your objective or the constraints, you can, in many cases, you just want some sort of polynomial time bound encode them by picking different functions.
You have a question, though I'm actually slightly confused. It's Georg is asking, is this bound UE or mu E?
Yeah, sorry, that should be a UE. Yeah.
Yeah.
Not a path parameter, just an upper bound on the capacity constraint. Thanks for the question. That follows from different works of use different notation there. Thank you for the catch. Any other questions? All right, so that's about it on the log barrier. How do we improve this analysis? And the next thing we'll be talking about is how to get improved iteration complexities. So how to improve the number of edges, the number of vertices. All right, so let's start by a geometric picture of summarizing what we just said. So these methods that we just discussed that are like root n iteration methods for solving linear programs with n constraints, they worked with the logarithmic barrier. In this particular case, the center of the polytope, the thing that just minimizes the logarithmic barrier, has a particular name. It's known as the analytic center of the polytope. We just proved that the Deacon ellipse is an n rounding of the polytope, and that this gives a root n iteration algorithm. All right. Now, our question is, we want to improve this. We want to improve this root n to a root of dimension. And before doing that, I want to note that perhaps we shouldn't be too surprised that the logarithmic barrier, in the worst case, has some sort of dependence on the number of constraints, rather than the underlying dimension. And to see that, note that the logarithmic barrier, this barrier function we're considering, that's just basically the sum of minus log of the distance to every one of the constraints, or sum of log of 1 over the distance to every constraints. Note that this barrier function really depends on the representation of the polytope. Like, it's not just a function of what the feasible region is, but it's a function of how exactly we chose to represent it in our matrix A. And to see that, suppose what we did is we took the same polytope, but in A, we just duplicated some of the rows. Or in other words, we just added some of these constraints a few times. That doesn't change the feasible region. However, it does change the barrier function, and it does change the central path, right? It essentially means that in the choice of how a polytope is represented, we could essentially be working with some sort of weighted log barrier. rather than the logarithmic barrier. If you repeat constraint I k times, then that's like putting a value of k in front of this log term. All right, so that means there's this degree of freedom, and it's not too hard to see this could really change the central path and the performance of the method. So that means that there's a sort of a degree of freedom that, an adversary and their choice of how they represent a polytope could change the central path and make things take more time. And that freedom, the budget of it has to do with the number of constraints they add, perhaps. Right. This also gives a natural idea for trying to design improved methods. If the weights on the log barrier kind of come from problem representation, and there's something that in the representation of the problem could have been chosen to slow down our method, then perhaps what we should do is optimize over these weights, try to pick a better weighted log barrier and get faster methods. Right. In joint work with Yuntat, we called this pathfinding as a homage to a previous paper. But this idea of using weights or using weights to kind of weighted log barriers actually arises in a number of different contexts. It's a key thing we used originally for a root deiteration method, and a number of different combinatorial advances in max flow and in cost flow also use this idea of a weighted log barrier in different ways. And also could argue has shown up implicitly in a variety of primal dual central path methods historically. All right. So this is the first approach we'll take towards trying to get a faster method. And before doing that, maybe the first question to ask is why really hope for a root deiteration method? So yes, we know that there is a D self-concordant barrier, but I also said computing it's very, very expensive in the worst case. Can we get some other intuition of why we could hope for a root deiteration method? And one way to see that, to get to some reason, is it's actually known. So we prove that the Deakin ellipse of the logarithmic barrier at the analytic center is an n rounding of the polytope. However, there's a classic result in convex geometry that says every convex body, including a polytope, has a D rounding. There is an ellipse inside the polytope that when you scale it by a factor of D, it contains the entire polytope. And the maximum volume ellipse is such a rounding. This is known as the John ellipside. Nice result of first John. All right. However, relevant for our discussion, interestingly, you can also show that this ellipse, this Deakin ellipse, is actually realizable as the Deakin ellipse of the weighted log barrier for some choice of weights. So at least for this thing of getting a rounding, there is a choice of weights where we could minimize the weighted log barrier and get a D rounding of the polytope. And this yields one natural candidate barrier you might try to look at to get a deiteration method. Just pick the weights to be the weights that somehow give a John ellipsoid. All right. Unfortunately, working with these weights is very unstable. And while this has the right rounding properties, unfortunately, as we move our point, these weights might change very quickly, and it's not quite clear how to use it to really get something like self-concordance or something where the weights don't change too much and we actually get a stable method. So what we're going to do to try to improve this is maybe we'll take a slightly different approach. Let's just take a look of what properties we want of the weights in order to get a root deiteration method locally. Let's try to get a more, rather than just thinking about the John ellipse, let's try to think a little more globally about what do we want the weights to, properties do we want of the weights, so that essentially the self-concordant analysis we've done before still kind of locally works out, just maybe with a better dependence on the number of variables versus the number of constraints. All right, so this is the setup we'll consider. Let's go back to our pathfinding method. Let's use the weighted log barrier, where P sub W of y is just going to be the log barrier. We put this term wy in front of every barrier term. And let's now try to bound the similar sort of properties that we bounded before from self-concordance in general for the weighted log barrier. Okay, any questions so far? The plan makes sense?
Yeah, I guess I was just curious, I guess it's still open whether there is a choice of wave function per point that actually gives you something that depends only on dimension. Or is that not? Is that not?
Maybe hold that thought. Depends how you want to phrase that question. If you just want a set of weights where the gradient of the weighted log barrier corresponds to the gradient of a self-concordant barrier at sectional path points. We'll actually show how to do that.
Okay, cool.
But the trick is that ultimate barrier is not quite a weighted log barrier. It's a different barrier that just the optimality conditions induce that.
Okay.
But this will maybe be clearer as I proceed.
Okay.
But great question. All right. Okay, so first thing we'd want to bound. We said that when we increase the path parameter, how much centrality increases has to do with what the gradient of the barrier is in the Hessian inverse norm. And I claim there's a nice bound. We can show this is at most the L1 norm of the weights. Again, in the interest of time, I'm not going to go through too much of the algebra in these lectures. I'll just say how the proof works. The proof is compute the gradient and the Hessian, do some algebraic manipulation to write out what the gradient, the quadratic form of the Hessian inverse with the gradient is. And what you'll get is the weight matrix, the square root of the weight matrix applied on either side to some sort of orthogonal projection matrix. And orthogonal projection matrices have eigenvalues at most 1, so they're at most the identity. So this quadratic form is at most 1 transpose W1, which is the L1 norm of W. That's the proof. Again, I'm just not going through the algebra in class because it takes a bit longer. I think it's good to go through on your own, and I'm happy to update the notes. Same reason I wasn't checking the algebra earlier. All right, that's roughly the proof. All right, what was the second property needed? So this was one thing we needed for a self-concordant barrier. The other property we wanted was that somehow the barrier doesn't change too quickly, right? We wanted that when we took a Newton step, the Hessian doesn't change too much. Now, the Hessian of the weighted log barrier is just A transpose, the slack matrix inverse, the diagonal of the weight matrix, the slack matrix inverse times A. That's the Hessian of the weighted log barrier. Now, if we're not changing the weights, since this is just a diagonal matrix with 1 over the slack on every coordinate, if we can just show the slacks don't change too much multiplicatively over a step, that implies the Hessian doesn't change too much multiplicatively over a step. So if we just want to show that sort of Newton's method, the Newton decrement is going down, it suffices to show that we can bound how much the slacks change multiplicatively when we take a centering step. Right. And I claim that we can upper bound this multiplicative change. So this is the difference between the slacks at y minus x divided by the slacks at x. The L infinity norm is giving the largest ratio of this largest of this multiplicative change. So think this is the same as max over all I of, this is equivalent to 1 minus sy over sx, the ith coordinate of that. So it's the same as asking for the ratio to be not too far from 1 of the new and old slacks for every coordinate. And I claim you can upper bound this, how much the slacks change, by the Newton decrement. And this is good. This is usually what we're controlling in our path following methods. So this is something we control to not be too large, times this other term that I will talk about a bit more shortly, which is the max diagonal entry of this matrix. That looks close to a projection matrix, but it's not exactly a projection matrix. Right?
Sorry, Aaron. Here, is it important that you want to say that the weights don't change too much when you take a Newton step?
So the game we're playing here is we're keeping the weights fixed. We're not changing the weights. We're imagining we're somehow central. And we're asking, like, what can we increase the path parameter? That's what we did the previous slide. And here we're asking, can we take a centering step for the weights fixed? We haven't talked about
right. Sorry. Yes. What I wanted to ask is, does it really matter if it's a centering step or if it's a step that's inside the diagonal ellipse?
I mean,
I guess you're basically proving that no matter what step you take inside the diagonal ellipse is going to be okay because you have the Newton decrement as part of the bound.
Yeah. I guess more broadly to answer your question, like if we replace the gradient here if we replace the gradient here with some vector d, this would be replacing lambda with d in the Hessian norm. And the same claim would be true.
Yeah. Okay.
Just picking gradient, so I didn't have to do as much notation.
Sure. Sounds good. Mm-hmm.
Yeah, but the inverse is important to make it. Sorry. Yeah, I guess this is just, you could have just phrased. You're right. You could have just phrased this as the change in the Hessian norm. I'll think about it. Maybe that's a better way to write this in the note. This says you can bound any change by d. Yeah.
Yeah, I was just saying you take any.
But the proof is a little. The proof is a little nicer when you have the Hessian here.
Okay.
But you could probably, I think you're right, you could do it the other way, but I want to check.
Right.
What I do feel, yeah, if you made this an arbitrary d, yeah, you get d in the Hessian inverse norm. So yeah, I think the whole thing you get in the Hessian, but I'll check.
Yeah.
Was that the question?
Yeah, basically.
Yep. All right. The proof of this is we will just expand out what the step looks like. And for every coordinate, we'll try to bound the multiplicative change. We'll do an application of Cauchy-Schwarz and just write down the result. And that's the proof. Okay.
I mean,
now,
so from my recollection, this should just be the same thing as saying, like, yeah, as long as the Duycken ellipse is contained inside the polytope, this should be true. Isn't it?
Yeah, I guess this is, you can think of this as similar as trying to bound how far you can move the Duycken ellipse inside the polytope. I think that's right.
Okay.
I think these are because the yeah, I think because this infinity norm radius is the same as infeasibility, like slacks being larger than 1 is the same as being infeasible, I think. If there's some direction, and because of the symmetry, so if there's some direction, I want to double check there's not an issue about when you go in one direction and not the other. So if you say the symmetrized polytope around your point, then I think that's right. I'm a little less sure off the top of my head when you don't symmetrize.
I see. Yes. But I think the point is like, no, I mean, yes.
So,
yes.
But good question.
Yes.
So yeah, I think this is the same as the Duycken ellipse being inside the symmetrized.
Symmetrized polytope, yeah.
Yeah. Which I guess implies you're inside the polytope, but if and only if. Anyway.
Yeah. No, I know what you mean.
Okay. All right. Good question. Anyway, what I want to do now is actually talk about what these conditions are. And I think a nice way of thinking about what this condition says, what this bound is through something known as leverage scores. And leverage scores, I think, are a very natural, fundamental, commonly occurring algorithmic concept, very useful in numerical linear algebra that arises in a number of cases where trying to get better dependence on dimension versus the number of constraints. I think they're a great concept to know. They generalize the notion of effective resistances in graphs, which some of you may have heard of. And yeah, they're a very, very useful notion for understanding rows of a matrix. Formally, leverage scores for a matrix A, that's an n by d matrix A. They're defined as the vector in Rn, where the ith coordinate, the ith leverage score, or equivalently the leverage score of row I, is simply the ith matrix of the orthogonal projection onto the image of A. Okay. So take your matrix A, make the projection on matrix onto its image. A times A transpose A pseudo inverse or inverse times A transpose. The ith diagonal entry of this is known as the leverage score of row I. All right. You can also think this is the same as the norm of row I in the A transpose A inverse norm. So you can think of it as you take your matrix, you imagine the change that would make the A transpose A become the identity. And under this change where A transpose A is the identity, you now ask what is the contribution of a single row to the identity. That's another way of looking at the leverage score. So it's a natural kind of multiplicative notion of the importance of a row. If deleting a row would make the rank of a matrix decrease, its leverage score is 1. And the leverage scores of everything else are between 0 and 1. And you can think it's this measure of contribution to this sort of properly normalized contribution to the matrix. Or, okay. Similarly, from this reasoning, you can show that the leverage score of row I is between 0 and 1 for every I. You can show the sum of the leverage scores is exactly the rank of the matrix, which is n most d. Sorry, Daniel, you had a question?
Oh, I just wanted to add another interpretation, which is that if you look at the image of A as a subspace, then the ith leverage score is, if you look at any unit vector in the subspace, it's how big the ith component can be in any unit vector squared.
Yeah.
So it's like yeah, it's another way of interpreting.
Cool. Thanks. Two other properties that are good to know. One, very useful in a number of contexts. We won't go into it too much today. You can show that if you sample rows of a matrix by their leverage score and appropriately reweight them, you only need d samples to make a matrix that only has O of d rows, where B transpose B is approximately A transpose A. And the other property that I'll just state, but that we'll sort of use, but I won't prove, is that you can compute multiplicative approximations to all the leverage scores by just solving a polylog number of linear systems in A transpose A, an additional nearly linear work. It's a very nice application of Johnson-Lindenstrauss that's very useful and maybe a good exercise to try to figure out how to do this for yourself. All right, but the point is, if we want to compute leverage scores exactly, this might take a number of linear system solves, but if we just want multiplicative estimates, this only takes a polylogarithmic number of linear system solves. Okay, and again, there are many nice properties. Daniel mentioned another. These are just a few that we'll use or maybe good to think about today. And the reason I define it is as follows. You can restate this lemma as saying that if you want to bound the multiplicative change, you can bound it by, when you take one of these steps, you can upper bound it by the Newton decrement times the largest ratio of the leverage score of row I under, when you rescale the rows of A by square root of the weights and the inverse of the slacks, and compare that to the weight itself. All right, so that's just a re-expressing of this just by multiplying by W1/2 and dividing by W. Okay. So in other words, how much the slacks change has to do with the Newton deck, like the step size you're taking. And this quantity that measures how off the weighted leverage scores are from the weights of the matrix. All right, so what weights does this suggest we might want to pick? Well, let's look at this again. Suppose we kind of normalize that it's sort of locally one self-concordant, like we normalize so that the weights are at least the leverage scores, right? If we do that, the L1 norm of the leverage scores will be, the weights will be at least the sum of the L1 norms of leverage scores, which will be at least the rank. So maybe what we should do is just try to pick the weights to be the leverage scores, right? Now, this idea of trying to pick weights to be the leverage scores, note this is a recursive definition. We're trying to set the weights to be the leverage scores of a row reweighting of the matrix that depends on the weights themselves. You can actually show what we're asking for here is an instance of a broader family of weights known as LP Lewis weights. And these are unique for all constant P, and they're defined as the weights that are the leverage scores when you reweight the matrix by a particular power of the weights. These particular weights we're asking for here, you can show Lewis weights are a natural notion of row importance in the P norm. Leverage scores are simply the special case when P equals 2. And these are a natural notion of like contribution of a row in the LP norm. You can show that when you sample by these weights, you again get approximations to the matrix in LP norm, though depending on the value of P, you might need to take a lot more samples. And interestingly, if you take P going to infinity, you get this condition, and you get these weights. And W infinity of A, this is actually the weights such that the ellipse they induce is the John ellipse for the set of AX being between 1 and -1. So in other words, picking weights that obey this condition is like picking a John ellipse for the set of, for AX being at most 1, we'll rescale every row of A by 1 over the slack. So it's kind of the John ellipse of the symmetrized polytope, where you constrain that no slack can change by where no slack can move by multiplicative 1. All right, so this is another way of actually seeing we get the John ellipse, just by looking locally at these conditions that we want. So, and again, you could ask the same question. Maybe we should just use these weights, these like L infinity or John ellipse inducing weights. And at first glance, it might actually seem like, unlike the other case where we just said, why not use these weights? It almost feels like we proved these weights work this time. We said, once you have these weights, you could center. And then we said, if you're center with respect to these weights, when you increase your path parameter, it behaves like a D self-concordant barrier rather than an N. So it almost feels like we just proved that this works. Unfortunately, there's a big catch here. And that's the big thing we haven't analyzed. And that's the question of how much do the weights change when we move X? So yes, at a single point, if we're central with respect to these weights, we can increase the path parameter and center again. But if we needed to change the weights to then make this property hold again, we haven't bounded that the weight change wouldn't be very large. And now the new normal gradient with respect to these new weights might be huge. In other words, we haven't really proven self-concordance. We've just kind of proven local self-concordance for fixed weights, but we haven't overall analyzed what happens as you change these weights. But there's a natural idea. W infinity seems like maybe very degenerate. We're taking the limit of these going to infinity. Maybe what we could do instead is pick a more softer, more regularized notion. Maybe we'll just pick the weights to be the LP Lewis weights just for a large value of p, like log n, but not going to infinity. In many applications, actually, it's helpful to pick the weights to not just be Lewis weights, but to be regularized Lewis weights. So something where the optimality conditions is this, plus maybe a little bit of a constant function or something like that. So you don't have to reason about weights getting super small. This often happens in many of the applications. And as I'll discuss in a sec, actually doing this works. So actually just picking LP Lewis weights, so the changes is a bit more smooth, actually gives a self-concordant barrier. What I mean by this is the following. You can prove that this barrier is self-concordant. Known as the Lewis weight, it's known as the Lewis weight barrier, or maybe the LS barrier, and it's just defined as follows. All right, so this is kind of a long formula, but I'll note that while it's kind of long, it's not very crazy. Maximizing W here, log det, this is like maximizing volume of a type of ellipse, subject to some penalty on how large the weights are. So it's in the genre of what we've talked about. All right, a few nice properties of this barrier. So first, I claim for all p larger than 2, the maximizing argument of this function is the LP Lewis weights of the appropriate reweighted matrix. All right. Now, what I'm saying is a self-concordant barrier is this function here that's defined as the result of log det of all of this for the maximizing weights. And I claim the following. If you look at the gradient of this function, I claim the gradient of this is exactly the gradient of the log barrier, where the weights are the LP Lewis weights. So Daniel, this is to your question before. This function is not a weighted log barrier, but to first order, its gradient is the gradient of a weighted log barrier for just a particular choice of weights.
Yes, no, sorry, that is what I meant, but it's not, like you still get some polylog dependence on the number of constraints.
Oh, sorry, yeah, for getting something that doesn't depend on the constraints at all, that's open.
Yeah, that was what I was, yeah, like, I mean, existentially or something, maybe not even efficiently computable. I was curious.
Other than the universal barrier, unfortunately, I don't have a great answer.
Yeah.
Other than
the universal barrier cannot be written this way,
methods. Huh?
And the universal barrier cannot be written this way.
It's a bit different.
Yeah.
In some sense, the way I think of it is this is kind of optimizing in the directions of the constraints, but doing it in sort of a more principled way. And the universal barrier is kind of optimizing in all directions.
Yeah.
And now, is there a good something in between? Is a very interesting question that's open. All right, a few more properties. The Hessian of this, you can also show as the Hessian of the weighted log barrier up to constants multiplicatively. So this behaves very much close to the weighted log barrier. And you can show that if you set P to be on the order of log n, this gives you, maybe I should say theta log n. This gets you a D self-concordant barrier. All right. Now, at this point, you might be asking, if you've looked at some of the papers, why are the papers in this line of work so long? Like, it doesn't seem like it would be that much, like this is a little bit of a complicated function, but shouldn't be that much calculus to prove this is self-concordant. And indeed, it's not self-concordant, but unfortunately, this doesn't quite solve our problem. Actually, computing the gradient of this barrier involves computing the Lewis weights fairly precisely. And if we want to actually get a method that only needs to solve a linear system, a few number of linear systems, we want to be able to just compute these Lewis weights approximately. As I said, even for leverage scores, we don't know how to compute them too precisely. So getting something to work with just a few number of linear systems require a bit more work, as does MaxFlow. The way the original papers or the journal version worked to do this is they kind of worked with the dual, the primal form of the problem, and showed how to work with weighted barriers for arbitrary one self-concordant functions on that space, and gave a theory for handling approximate weights. What I'm going to present in the rest of time I have today is a possibly simpler, more recent primal dual approach towards instead solving this problem. Okay, which brings me to the last part of the talk. Any questions? Okay. All right. So as I've hinted at or discussed a few times earlier in this lecture series, one recent thing that's been helpful in many advances is instead of just working with the dual or the primal, taking a sort of broader primal dual view for some of these methods. So to be a bit more formal, again, we're working with the weighted log barrier. We're considering the weighted central path. And we can imagine a variety of schemes where we change the weights and change the point and advance the path parameter. Now, you can show that there's an equivalent primal dual optimality criteria for being a weighted central path point, for being the central path point for the weighted log barrier. Equivalently, you can show it suffices to be the following, that you're a primal dual set of feasible set of points. So X feasible for the primal, so X that's non-negative with A transpose X equals C, and SY that are feasible for the dual. So S that's non-negative with AY plus S equals to B, and which then therefore implies that AY is at least B. All right. Now you can show if you have any primal dual feasible points with the property that ith coordinate of X times the ith coordinate of S is equal to WI over mu. That's equivalent to showing that SY are weighted central path points for the dual. And you could show that that also implies that X is a weighted central path point for the primal. And just as I mentioned before, that without weights, the primal and dual central paths to the log barrier are dual to each other up to something additive that just depends on the path parameter. Here, these are dual to each other up to something that just depends on the weights in mu. All right. And this suggests a natural approach. What we could try to do is just keep increasing mu for some bounded weights. All right, and this is a way we can maintain primal and dual points and try to move along the central path. All right, so let's think about towards trying to get maybe a simpler primal dual approach. Let's maybe think about what in primal dual space this Lewis weight barrier corresponds to. So suppose we have our primal dual set of points. What we said, the weights that correspond to the Lewis weight barrier we discussed, these are weights that are given by the LP Lewis weights of the constraint matrix weighted by S inverse. Okay. And in turn, we said the Lewis weights are the solution to this recursive equation of this recursive equation I wrote here. Okay. So this is just an equivalent way of describing the central path we were considering before. We want xs, where xi times si equals the weights wi over mu. And the weights obey this recursive condition of being LP Lewis weights with respect to s. Right. Now, for p between 0 and 4, there are fast ways of computing the Lewis weights everywhere just using a few linear system solves. For p larger than that, it takes a bit more work to compute the Lewis weights. It would kind of be nice if we could just work with leverage scores all the time. Leverage score is the thing sort of directly we have from this Johnson-Lindenstrauss trick we can compute multiplicative estimates for. It would maybe be nice if we didn't have to do as much recursive definitions. And it's a little perhaps annoying here that our central path optimality has this like recursive definition of Lewis weights baked into it. However, note the following. Maybe we should ask, do we really need Lewis weights? I mean, at the end of the day, what we want is just xs that's equal to 1 over mu w, where w obeys this condition. But this is recursive also in terms of w being defined in terms of s. Like we know here that w at optimality should just be xs. So we could substitute this back in, and equivalently, the optimality conditions for being a central path point are just that xs are the weights, where the weights are just the leverage scores of this matrix. This is just what you get when you take these weights and you substitute in the optimality condition that we know that weights should be x times s. So what this says is you can an equivalent way of defining the central path we just discussed is just to ask for x times s to be the leverage scores of this matrix weighted by x and s. And now there's still a recursive criterion in x and s here, but there's no extra notion of weights. We're just asking for the optimality conditions to be xs to be the leverage scores rather than arbitrary weights. Leverage scores rather than being Lewis weights. Note that if we had set w to be 1, this is the same as looking for set w to be 1. This is the same as looking for essential path points to a logarithmic barrier. And what this is just saying is the Lewis weight barrier is essentially working with a sort of leverage score, just reweighting of everything at optimality. All right. You could also show that things would work out fine if instead of using the leverage scores, use like certain regularized versions, which could be helpful. So I'll denote tau to be these leverage scores plus d over n constant multiple everywhere. It's like adding a little bit of a log barrier to the Lewis weight barrier. Helps to make some analysis nicer. All right. And note that with this definition, there are no Lewis weights. And note this is actually, though, the same central path. This is not a different path than the Lewis weight barrier, but it's maybe suggests different ways we could penalize the path or reason about suboptimality. All right. Interestingly, I should note here that unfortunately, this technique simplifies a bunch of the analysis for root deiteration methods and minimum cost transshipment. Unfortunately, this trick of getting rid of Lewis weights is not known how to work for things like max flow and min cost flow, which I might touch upon briefly at the end. Okay. All right, so what do we do with this? How does this help? Well, this enables us, having this nice primal dual form makes it easier to do a variety of apply recent techniques and robust methods that I think was really kind of codified in this work of Cohen, Lee, and Song. We could debate if it was, to what degree it was intrinsic in previous methods, appeared to some degree in previous methods. So the idea is the following. Now that we have these sort of primal dual optimality conditions, let's instead just do the following. Let's just maintain primal dual feasible points x and s. I'm just going to define wi to be xi, si. So this is a little change of notation from before. So I'm just going to think about what xi and si are. And what we'll do is we'll just have some penalty on wi being what it should be. So for the log barrier, wi should be the xi, si should be the all ones vector appropriately scaled. For the Lewis weight barrier, wi should be this. What we'll do is the following. We'll just maintain our arbitrary points x and s, and we'll just take Newton steps towards trying to make w get closer to the true condition. And maybe by picking a good penalty function, we won't need to maintain quite as central points as we'll maintain before, and maybe we can tolerate a lot more approximation in our method. Right? The way this worked in Conley and Sung and variants of it were used later is the following. I'm just going to let phi be a potential that's sort of a exponential penalty on v being far away from 1. And we'll simply set our potential to be the sum over all the coordinates of mu times phi of mu times xi si. So this is just some exponential penalty on having xi si actually being equal to 1 over mu. For the LS barrier, we'll do the same thing. We'll just divide by our tau, our leverage score function. Right? And the idea here is we'll use nice stability properties of the exponential function to try to argue that you actually, to get a method to work, you don't actually need to compute these functions too precisely or their gradients too precisely. Okay. So to be more formal, I guess I'll try to wrap up now by basically just saying roughly what the final methods actually look like under this approach. So here's what this enables algorithms to actually look like. What we'll do now is we'll just maintain some approximately feasible primal dual points. What we'll also do is maybe we won't always store these points explicitly, but we'll try to maintain multiplicative approximations to x and s. Remember, x and s are non-negative vectors. It makes sense to talk about maintaining multiplicative approximations to them. What we'll then do is we'll look at our penalty function, and we'll try to get some direction that would improve our penalty function. So we'll maybe also have computed tau, these leverage scores, multiplicatively approximately. We'll feed that all into our potential function, these approximations, and we'll compute the gradient with these coroute approximations. So this would give a direction towards making this potential function smaller and making sure the potential function is not too large and therefore we're central. What we'll also do maybe is compute some approximate Hessian induced by x and s. And with this, we'll take both primal and dual Newton steps of some step size. All right. So we have approximate points, approximate Hessian, and approximate Newton steps on x and s in this direction that came from this gradient of this penalty. All right. There's one other issue here that occurs that when we do this, our primal points might no longer be feasible. And essentially different works have addressed, some of the recent works have addressed how you would handle the loss of feasibility here in different ways. Right. But at a very high level, this is the entire idea of the method. Pick some penalty function on centrality, on xs being the values you want, maintain all your iterates approximately, show that approximate maintenance of the iterates is enough to get a good direction, and that taking steps with these approximations suffice. And what this says is as long as we can really maintain these xs approximately, we might not need to write down the true x and s, but we can figure out the steps we needed to take and get the iterates we want. Right? And this is the rough method.
Aaron?
Yep.
So let's say, is there a way to, let's say, exactly express, standard path following with the logarithmic barrier in this penalty framework, but maybe not with an exponential, maybe with something different?
Yeah, I think more standard path following, it would, I don't know about exactly, but it'd be very close to just picking phi to be the L2 norm.
Oh, wait,
yeah, it'd be like picking these, it's like picking these individual components to be quadratics. It's maybe not exactly that, but it's something fairly close to that. Like the normal notion of centrality and being able to center, it's kind of asking for the sum of these differences to one. Sorry, it's basically the penalty would be the sum of these differences and one, and L2 norm being at most one.
Right.
I need to think about whether that's kind of, I'm not sure it's exactly centrality. Sorry, it's not going to be exactly primal or dual in that the moment both are approximation, you've done something a little different. Like,
oh yeah,
I think for like for once you have like y and s, when you work with the gradient, that's not exactly x. It's like something kind of approximated by x, but not exactly x. So that picking it to be L2 norm would behave very similarly, but I don't think you get, I need to think, I'm not sure you get exactly the same method. But the analysis is very similar to that.
Right, I see.
Yeah, good question. All right, and that's the method, and that's the idea behind these robust methods. And what this enables now is all we need to be able to do is maintain these multiplicative approximations. And this is now in turn the entire question of getting a working interior point method, whether a root n iteration 1 using this or a root d iteration 1 using this, to the data structure problem of can we maintain all of these approximations. Yeah. So again, this gives a root d iteration method. I also want to note that the proofs then that this is a root d iteration method, sorry, this should be V, are actually not that long. All you need to do is show how to pick D and then just analyze the steps. So it gives a not too long proof of these number of iterations, like an M root n min cost transshipment algorithm. Gives a not too long proof and a not too long algorithm, just using linear system solvers and computing the leverage scores approximately as you need them. For two-sided constraints, you need to do a bit more work. Unfortunately, exactly this doesn't work. Essentially, the key difference is rather than doing the fully primal dual thing, kind of instead more work with the primal and maintain weighted two-sided barriers weighted by L1 minus delta Lewis rates. But we kind of use a primal dual formulation to talk about the error in that space. So it's a different potential function, and you do have to use Lewis weights. But Lewis weights you can compute. All right, so that's it on what I want to say about interior point methods as methods themselves. I just want to say a little bit about just a minute or two about how you actually implement these methods. So how do you actually implement these to get fast methods? You might also be asking, like, why, if you've tried to look at some of these recent papers I've been describing that get near linear time algorithms, why are they all at least 100 pages? Hopefully this has conveyed the sense that the actual analysis of the interior point methods is not that long or that complicated, and neither are any of the individual pieces. It's just to turn everything I just said into an actual algorithm that can run in near linear time. You need to show that you can get data structures for maintaining all of these things in sublinear time. And every data structure requires a little bit of writing, at least first pass. I think one of the big conceptual leaps is showing how you can maintain the iterates multiplicatively in sublinear time, which we called vector maintenance. You also need to build data structures for computing, maintaining leverage scores, and computing the gradient. In the case of Maxwell, you want to maintain Lewis weights. There's also data structures from this longer line of work I mentioned on maintaining the inverse. Different works have different ways of maintaining or handling feasibility and sampling, and every one of these pieces to ultimately get the runtime you want is some writing on a data structure. So there's just many ingredients. Although in my very biased opinion, no ingredient, I think each ingredient is sort of manageable. I'd be happy to talk about this a bit more. There's, I think, a variety of interesting techniques in some of these pieces, but I think that's for another talk. I wanted to focus this series a bit more, I guess, on the interior point methods themselves that reduce linear programming and these combinatorial problems to these data structure problems of maintaining each of these pieces. Oh, and you also have to worry about additional points and rounding and things like that. Yep. All right. So that's about it for this. Again, the goal of this talk was to give you a sense of what the key techniques and give you some mathematical underpinnings for what these techniques look like. Hopefully this gives you a sense of a variety of work in this space and gives you some tools if you want to check out these results or build on them to solve some problems of your own. So thank you all for your time and the great questions, and I'm happy to stick around for more. Thanks, everyone.